Okay, so we are discussing more about section 6.6. We were looking at tank problems, and here's example 4 in section 6.6. Work needed to empty a tank. So we did one problem already, and here's a problem from the book. So let's take a look at this problem. So we have a tank that has the shape of an inverted circular cone with height 10 meters and base radius 4 meters. It's filled with water to the height of 8 meters. They want you to find the work required to empty the tank by pumping all of the water to the top of the tank. Okay, and they're telling you here the density of water is 1,000 kilograms per cubic meter. So this problem is different because, well, for one thing, tank is different, but also your units are different. The previous problem, we had work was going to be in foot-pounds. Here, what's work going to be in? What units would work be in for this problem, given the metric units? The final work answer, the units would be in not foot-pounds. Okay, so Newton meters would be what, Taj? Newton meters would be joules. That's right, Mario. So both Taj and Mario are right. Joules, good. So okay, first of all, let's look at this problem. Let's look at a picture. Let's look at a picture. So I'm going to go down here to figure 3, and here's a picture of the tank. And the tank, again, it's an inverted cone. So the tank, they have there a layer of water. It's in purple. And this time the layer of water is not like a brick shape, okay? It's a cylinder shape. So we're going to need to find the volume of the ith layer of water, which is going to be a cylinder. The ith layer of water, that pink ith layer of water, is a distance of xi meters from the top of the tank. You know, the water would be pumped out of the top of the tank. And there's some radius, r sub I, for that ith layer of water. And that radius naturally is going to vary depending on how far down your ith layer of water is. And then the ith layer of water has a width of delta, or a height of delta x. Okay, so naturally what we need to do, we first of all focus on, I got to be able to find the volume of the ith layer of water in terms of my variable x. So that radius there, that radius r sub I have to find out what that equals in terms of the variable x, which is the distance that the ith layer of water is from the top of the tank. So, okay, here we go again. We're going to use similar triangles to help us. So in this problem, you have 2 similar triangles. You have a big triangle which has that's the big cone. If we look at the front, if we look at a side view of that cone, it's a triangle. Okay, it's a triangle with radius 4. Okay, because it says the base radius is 4 meters, and the height is 10 meters. Now the little triangle there, which is the triangle determined, well, if that ith layer of water is xi meters below from the top, then that little right triangle would have to have a height of 10 minus xi meters. So, and then there's your radius r sub I. So if we take the, I want to say this the right way, if we look at and there's different ways to do these proportions, but if we were to look at the radius r sub I relative to the height of that little right triangle, which is 10 minus x sub I, that would have to equal 4 over 10 by similar right triangles. And so you end up getting that r sub I over 10 minus x sub I is equal to 4 over 10. And then you can solve for the radius. The radius r sub I would equal 2/5 times 10 minus x sub I. Okay, are there any questions on that? All right, well now what we have to do is find the volume of the ith layer of water. We know the volume of the ith layer of water. The ith layer of water is a cylinder, right? So the volume of a cylinder is pi r squared times the height. So, okay, we know the height is delta x. We know the radius is 2/5 times 10 minus x sub I. So the volume of the ith layer of water would be equal to pi r squared times delta x. If we square that 2/5 times 10 minus xi, that would get us 4/25 times the quantity 10 minus xi squared. And now you have the volume of the ith layer of water. So are there any questions there? You see how they're breaking in this example 4 from section 6.6. You see how they're breaking the problem up into like pieces and going from one piece to the next. Now that you've found the volume of the ith layer of water, the next step, of course, is to find the force needed to bring the ith layer of water, raise it to the top of the tank. But in this problem, because you're dealing with metric units, okay, we have to work with then acceleration due to gravity. Force equals mass times gravity. But to get the mass, you have to realize that mass equals density times volume. Okay, how many learned that density is mass over volume? How many remember that from like maybe high school or middle school? Density is mass divided by volume. That's a very common formula. Sure. Well, if density is mass divided by volume, then mass would be density times volume. Well, what's the density? What's the density of the water? The density of the water is 1,000 kilograms. So now I'm looking, let me see, now I'm looking here. The density of the water, and let me see, hold on, it's, sometimes when I highlighted it, makes it look funny. Let me just see if I can maybe just do it, not highlight it when I make it bigger, that's better. Okay, so the density of water is 1,000 kilograms per cubic meter. I'm going to take that 1,000 and multiply it by my volume, which is 4 pi over 25 times 10 minus xi squared delta x. If I simplify that, the mass for the ith layer of water is going to be 160 pi times 10 minus, that's a 10 there in the little, like to the right there, after the 160 pi, that's a 10 minus xi. So 10 minus xi squared delta x. That's, so the mass is 160 pi times the quantity 10 minus xi squared times delta x. The force required to raise this layer must overcome the force of gravity. And so now the force due to gravity is this here. Mass times acceleration to gravity. Gravity is 9.8 meters per second squared. We multiply that by, that's the gravity. We multiply that by the mass. And that's going to get us 1,560. The force to, on the ith layer of water is simply going to be 150/68 pi times the quantity 10 minus xi squared times delta x. Are there any questions so far? Okay. Well, now, okay, now we need to find, now that we know the force for the ith layer of water, we need to find the work needed to raise that ith layer of water to the top of the tank. Well, when we have work, work is force times distance. So if you look at the way they have the picture, they've developed the picture, the x sub I in figure, well, it's figure 3 here. X sub I is the distance that the ith layer of water is from the top of the tank. So to get the work needed to raise the ith layer of water to the top of the tank, you're just going to take the force times the distance x sub I. And that will get you then, that'll be 1568 pi times xi times the quantity 10 minus xi squared times delta x. Are there any questions on that? All right, well, then finally then, to find the total work, let me see here, let me, if I can highlight this. To find the total work done in emptying the entire tank, we're gonna add up all the little pieces of work. So we get the Riemann sum. You know, we get this. I want to maybe highlight it. Let's see, can I highlight it? Forgive me one moment. It's a little picky on how to highlight. There we go. Let's put that in pink. Okay, so the work needed would be the sum of all the little pieces of work. And so we take the Riemann sum of all the little w sub i's, those pieces of work, and go to infinity. Okay, and actually, hold on one moment. I'm going to put that actually in yellow. Okay, and as n goes to infinity, that makes the Riemann sum become, here we go, an integral. Now, the integral goes from 2 to 10, 2 to 10. Why would that be? Why would the integral go from 2 to 10? We're almost done here. Just give me 1 or 2 more minutes. It says that the tank's filled, it's filled with water to a height of 8 meters. Okay, the tank is filled with water to a height of 8 meters. So how the top layer of water, if you look in figure 3, how far does the top layer of water, how many meters does it have to be lifted to get out of the tank, the top layer of water? How many meters? That's right, Mario, 2 meters. That's right, Jan. That's right, Ange. Okay, now the bottom layer of water at the bottom, how many meters does that have to be lifted to reach the top of the tank? You know, once the layer is lifted to the top of the tank, the work's done on that layer. So the bottom layer of water has to move 10 meters. That's right, Ange, 10 meters. That's right, Sandia, 10 meters. And so therefore, the limits go from 2 to 10. And now, you know, you square the 10 minus xi, you'll get 100x minus 20x squared plus 100x minus 20x plus x squared, but you're multiplying that by x, so that gets you in the integrand there on the second step, 100x minus 20x squared plus x cubed. You do the integration, you get your answer, and what they've done is they've written the answer in scientific notation. Scientific notation. Okay, and there you go. There you go. There's your answer. Are there any questions on that? And let me just check one thing real quick, class. One moment. Just give me one moment here. This will take just one moment. I want to check one thing while I'm at it. One thing. I'm not looking at my email. You hear email, but I'm not looking at it. I'm looking at the assignment. I'm checking one thing out from this 6.6 set of exercises. Checking one thing out. No, okay, that's fine. That's fine. Okay, so are there any questions on this? Are there any questions at all? Who's feeling good? Who's feeling good? Who's reasonably comfortable? All right, Taj, excellent. Excellent. Thank you, Jensen. Thank you, Taj. Okay, great. Well, I thank you for staying a few minutes extra of time. Let me stop the recording.